Hello and welcome to the third and final tutorial on the evaluation of wide-angle scattering data of non-graphitic carbons using Octave. In this tutorial, we will deal with the actual refinement and evaluation of the scattering data. The prerequisite for this is that Octave has already been installed and set up, and a suitable iops.oct file has been found or created. Both have already been described in the previous videos. For the refinement, the file's fit routine, iops and, of course, the scattering data are required. In this example, the measurement data is in 2 theta and goes from 10 to 140 degrees. Let's take a look at the script first. In the upper block, you can see the microstructure data, which should be refined. Below this, the concentrations of disordered carbon and photon atoms can be entered, which are known, for example, from XPS measurements or in elemental analysis. In this example, we want to first refine the data manually. In addition, parameters such as the name of measurement series, the file name of the script used, the path of the script and the oct file, as well as the path of the measurement data must be specified. It must be ensured that the correct separator is used for the path. Since this is an X-ray scattering example, no further corrections need to be made for the background. The wavelength is already preset to copper radiation. The intensity is plotted against 2 theta. No points should be skipped at the beginning or the end, but only every fifth point should be calculated in order to speed up the calculation. Finally, the absorption and polarization is taken into account. It is assumed that the sample is approximately graphite with a density of 2.2 grams per cubic centimeters with a sample thickness of 3 millimeters. It was measured in fragmentano and not in transmission geometry. In addition, the beam is not polarized. Instead, the mean value of 0 to 360 degrees is used to calculate the polarization effect. If the script is now started, a plot is displayed which contains the measurement data and the simulated intensities. This data is also saved on the hard drive. In this case, an ID has not yet been set for the sample, which is why the directory name is ID. This should be unique for each sample. If the ID is changed, however, the data will still be saved in the same path. To apply the changes, Octave must be restarted. To do things simple, the script is copied and renamed. In the new file, the ID and the file name must be changed again. The parameter ID must be changed before a new execution. The data are now saved in a separate directory. This directory contains the image with the plot, the microstructure parameters used, and a table with further parameters and the measurement and calculated intensities. A copy of the script used is also saved so that it is clear how the data was calculated. To begin the actual refinement, the file is copied again. If you look at the fit, both the constant background and the normalization of the intensity are too low. Both values must be increased. In addition, the concentration of oxygen and sulfur is known in Android. For the next step, a new file is created. In the following, the further procedure for a complete manual adjustment is explained, followed by the automatic adjustment. For manual refinement, the parameters for the interlayer scattering, that is, for the scattering of the stacks, are first refined. The most important parameters are the stack height, the mean and minimum layer distance, and the standard deviation of the distances. The stack height can be calculated from the parameters mu, beta, and A3. Since the O2 reflection is currently too large, e.g. beta can be increased. This makes the reflection smaller and wider. Since the reflection is now too shallow, mu is increased. The reflection shape now roughly fits. At the same time, however, the background is too small and has to be readjusted. However, there is still a large discrepancy at very low values of the scattering vector. That is because the stacks are not uniform. The stacks can be larger or smaller, but layers within can also be shifted or twisted. To take this effect into account, the parameter eta is set to a value less than 1. Overall, the range between the O2 and the 1O reflection is still not well adjusted. This is due to the fact that the interlayer scattering, that means the scattering of the individual graphene layers, has not yet been refined. To do so, the file is copied again and the ID in the file name In the case of layer structure, layer extension and the standard deviation of the bond length are the most relevant parameters. Since nu is set to a fixed value, only alpha has to be refined for the layer size. Overall, the 1O reflection is too large, which is why alpha has to be increased. At the same time, the 1 reflection is still too high. This effect suggests a higher disorder, which is why sig 1 is increased. After further optimization of the background and the normalization of the intensity, this step has already been completed. As the last step of the manual refinement, all parameters should now be refined at the same time. For this, the parameter nskip is set to 1 in order to display all measured points. Since the O2 reflection is still too narrow and too high, beta is increased. If one looks at the O2 reflection, it is noticeable that is hardly visible in the measurement data, but very strongly in the simulated data. To fix this, parameters dA3 and sig3 must be increased. Together with the final adjustment of the background and the normalization, the simulated intensity now agrees with the measurement values. The manual adjustment is now completed. The result is saved on a hard drive and can therefore be easily read. Step 2, the rough adjustment of the background, is used as to start for the automatic refinement. Since no longer just a single plot but an entire refinement should be output, the parameter plot only must be set to false. The script now refines the data fully automatically in the same order in which it was done manually. Images of the result, the deviation between measured and calculated intensities, and images of the individual fit levels are outputted. They are also saved on the hard drive. A manual refinement can then be carried out. A new file is created for this. The result of the previous refinement is used as the new starting values. This data can simply be copied into the script. In addition, float only must be set to false again. Since the result of the automatic fit already matches measurement data, no further manual refinement has to be done in this case. The measurement has now been fully evaluated and the max factor determined.